Lesson 57, Ideal Gas Law. So when we're considering gas in mathematics, it's not the liquid gasoline that we put in our automobiles to make them run, but it's the gas, like oxygen is a gas that we breathe. You might think of this picture over here on the left, a helium tank. A tank is full of helium to blow up balloons. When you grill, if you have a gas grill, you use propane. Propane is a gas in the tank, or maybe some of you guys live outside of city limits and you need a propane tank to fuel stuff in your house. Okay, that's the kind of gas we're talking about. So it just so happens that gases follow laws. You'll learn more about this when you get to physics, but we'll learn the mathematics of it now. Gas has three components. Gas has a pressure, a volume, and a temperature, and they're all related in this ratio. So the product of the pressure times the volume divided by the temperature. That ratio of those values that you have at the beginning, so your initial conditions, if you change one of those, the pressure, the volume, or the temperature, okay, so you hop over here to the right side. So the sub 2 means your final conditions or conditions after you change. The ratio is always going to be the same. Okay, so when you put in those numbers, you have equality on the left and the right. You can go in and mess around with the pressures, the volumes, the temperatures, and change all that. But at the end of the day, those ratios will always be equivalent. We have some new units to talk about regarding gas and the gas laws. If you have your book, you can open to page 245, and let's go through these quickly because you need to know these. Pressure, the pressure volumes for gas. So on page 245, right about in the center, it tells us the pressure units. Probably the most common one is going to be something called newtons per square meter. And that's going to be abbreviated by newtons as a capital N. Okay, that's a measure of force. Okay, kind of like pounds, it's a force. Per is the division bar, and then square meter. Newtons per square meter. All right, the other one that's pretty common is called atmospheres. And that's going to be abbreviated just ATM. The other one in your book is, it says millimeters of mercury. I haven't ever seen that used in this book, but we'll write it out anyway. Millimeters of mercury is a pressure. Okay, we do see this one in the book, a pressure called torrs. And then finally, we have pounds per cubic inch. So obviously we would abbreviate that one, pounds lb per, and then cubic inch. All right, so we need to know whenever your book talks about these units, those are always pressure units. Next is volume. My volume units are always going to be in, now these aren't necessarily new. You have volume units, either milliliters, liters, or cubic centimeters. And then finally, temperature. This is a new one for you guys. Temperature with gas is measured in kelvins. Okay, now kelvins, when we talk about temperature in kelvins, we do not use the degree symbol. Okay, degrees is, so no degree symbol. That's reserved for degrees Fahrenheit, degrees Celsius. So if we have a temperature in kelvins, let's say, for example, 0, we would just say 0 Kelvin. Okay, not 0 degrees Kelvin, just 0 Kelvin. This is actually a special temperature. It's called absolute value. Have you heard of that? Absolute zero. Absolute zero is 0 Kelvin, which is equivalent to -273 degrees Celsius. Super, super cold. So that's just kind of an interesting little factoid there. Also, when you get to physics, when you're doing newtons per square meter, that's also referred to as Pascal. Okay. However, in mathematics, we're not going to use Pascal. You'll do that when you get to physics, but we're just going to do newtons per square meter. All right, so those are all of our units. This formula, got to memorize it. Okay, memorize that formula. PV over T equals PV over T. Just remember that the temperature is always in the denominator. Temperature is on the bottom. That brings us to example 1. Let's begin reading. 8 liters of an ideal gas at a temperature of 1000 kelvins had a pressure of 200 newtons per square meter. All right, I'm going to stop there. We've got 8 liters. Okay, liters refers to a volume. So that's my V1 of an ideal gas at a temperature of 1000 kelvins. That's my temperature, T1. And had a pressure of, okay, this is my pressure of 200, and that's given in newtons per square meter. So that's my P1. Great, so let's go ahead and start writing out this formula. Remember, we've got PV over T equals PV over T, and you want to make sure in subscript, 1's on the left for your initial conditions, and then 2 on the right for your changed conditions, or your final conditions. And we have everything we need for the whole left side. We have all of our initial conditions. Our P is first, pressure is 200. V1 is next, that's our volume of 8. Now you can leave the units out when you're just sticking in the numbers. Okay, the units aren't going to change, so we'll just insert the units at the end when we've solved it. And then our temperature of 1000 kelvins. Okay, great. Let's continue reading. If the volume were increased to 10 liters, okay, so this is my changed condition. That's my volume changed V2. And the temperature reduced to 800 kelvins. That's my T2, final temperature, comma, what would the pressure be? P2. So that's what we're solving for right here. All right, that's what we're solving for. So let's continue substituting on the right. We have P2, that stays the variable. V2 is 10. T2 on the bottom is 800. All right, we can do a little bit of this by hand, can't we? So 10 goes into 800. Let's cross off one of the zeros. All right, P2 over 80. Let's isolate P2 by multiplying both sides by 80. Okay, and let's see. We can do a little bit of this by hand, right? We've got a bunch of zeros. I'm looking at the left side. I've got 1, 2, 3 zeros in the denominator, so let's cross off 1, 2, 3 zeros in the numerator. So 8 times 2 times 8, 64 times 2, is that 120? 126? 120, 128. So 128 equals P2. We'll leave a little bit of space because we need to go back and stick in our units. So we're looking for units of pressure. Go back up to the text, see if you can find it. Had a pressure of 200 newtons per square meter. Newtons per square meter. So capital N over M squared is my final pressure. Let's do another one. Example 2. The temperature of a quantity of ideal gas was held constant at 1400 kelvins in an experiment. All right, oh, wait here, just wait, stop here. This is important. The temperature was held constant. This is important. If you see this key phrase, was held constant. Okay, that means, let's see, temperature was held constant at 1400. That means that T1, my initial temperature, is the same as my final temperature. It was held constant. So we have equality. Well, let's see what exactly that does in our formula. So PV over T, if T is 1400 to begin with, equals PV over T, and my final temperature is also 1400. Take a look at this, just mathematically. Look at that. What happens? What happens if my denominator is the same? When we have a ratio equals a ratio? Dylan? Exactly. They cancel, don't they? And then the numerators must be the same. Let's just kind of do this mathematically and just prove that this is true. So if I want to get rid of the fraction on the right-hand side, I would multiply by 1400. What I do to the right, I have to do to the left. And let's see what Dylan says is true. Check it out. They both cancel. So therefore, what happens is if you have one of your components or one of your variables held constant, in essence, it just omits it from the formula altogether. So that's pretty cool. I'm going to hop over a couple of slides so you can look at this. You can write it down if you want, but as long as you understand it. Let's read together. Sometimes we will be able to omit one of the variables because some part of the experiment is held constant. So if you see that phrase, is held constant, then you have what we just encountered. Okay, so when the temperature is constant, guess what? The T's drop out. Remember our original formula, PV over T equals PV over T. One's on the left, two's on the right. Okay, so if temperature is held constant, you simply just delete them or omit them. This is what it's going to look like if the pressure is held constant. The P's are gone. This is what it looks like if the volume is held constant. The V variable is gone. Okay. Now, each one of these individual little formulas has a special name. However, in mathematics, we're not going to concern ourselves with that. You can learn more about that when you get to physics. Okay, but mathematically, you're looking for that key phrase, is held constant, and if so, you can omit that variable. All right, let's continue reading. The original pressure was 11 atmospheres. So that's our pressure units. So that's P1. No, sorry. The original would be sub 1, P sub 1. And the original volume was 44 liters. V1. All right. if the volume was reduced to 4.4 liters, volume was reduced. Okay, so that's the final condition or the changed condition, so V sub 2. What would the final pressure be? So again, we're solving for P2. Now, find P2 in the formula, and I'm going to encourage you all, okay, to solve this abstractly for the variable first. So let's put some of this abstract solving to practice that you guys have been doing so beautifully in previous lessons, right? If I want to get the P2 by itself, what would I do? What would I do to get P2 by itself? Somebody raise your hand. Tell me, how would I get P2 by itself? Okay, Robel, go ahead. Exactly, we're going to divide by V2. Good job. Great. So now that's going to make it so much nicer when we do our math. Okay, so on the right side, we just have P2 equals. And now we can substitute in our known values here. P1 is 11 times V1, which is 44, over V2, which is 4.4. Okay, so if you're using your calculator, this is nice, right? Because you can just put this in as a single entry in your calculator and just go for it. Okay, or it makes it easier to solve by hand as well. So what we get here is 110. So leave a little space because we're going to have to label. So this is a pressure. Who can tell me what my pressure units are in this instance? All right, Dylan, what are my pressure units? Atmospheres, good. Okay. So ATM. Great job. We'll end with example 3. The initial pressure of a quantity of an ideal gas was 400 newtons per square meter, and the initial temperature was 1200 kelvins. The volume was held constant. Woohoo! V1 equals V2, folks. What does that mean? You can drop the V's from the equation. So here we go. We've got PV over T, but we're going to drop the V and just do P1 over T1 equals P2 over T2. All right, we've got initial pressure is 400 newtons per square meter. That's my P1. Initial temperature, 1200 kelvins. Volume held constant. What was the pressure? What was the pressure? That means we're solving for P2 again, coincidentally. Keep reading. If the temperature was decreased to 900 kelvins, all right, that's my change. That's my final conditions of temperature, T2. Okay, we're solving for P2. So Macy, can you tell me how I would get P2 by itself? Perfect. Multiply by T2 on both sides. Great. All right. Love it. So on the right side, I just have P2 beautiful equals. And let's see, somebody tell me what I should substitute in for the left side. So let's see, Noah, could you do that for me? Does your mic work? I'm going to substitute the left side. So first we're going to do T2. So go back up here. What was the final temperature? Okay, so we're just going to put in 900. We'll leave the units out. And then what's my P1? Great. And the denominator is T1. Great. And again, we're going to leave off the units while we're just doing the pure math, and we'll add the units at the end. Isn't this great? So you can just stick this right in your calculator if you want. You could do a little of this by hand if you want, right? We got 2 zeros in the denominator. Cross off 2 of those there. So it's like 3,600 divided by 12. And anyway, that would just be a single calculation, which is nice. All right, so 300. And Rowan, could you look back up at the text and find the pressure units? What are the pressure units that we're using? Beautiful. So that's a capital N over M squared. All right, guys, that is the ideal gas law. Good job.